So we'll go through and draw some starts. So remember reaction coordinate, what we're looking at is how we convert from our reactants to our products. So one of the first things that I saw was something along these lines. Start simply. What's wrong with it?
So like one step.
Okay, too hard. Let's make a modification there. Okay, now let's start simply. What's wrong with it?
It's not exothermic.
Okay. Given the context of the information given to us, we know this reaction is supposed to be exothermic. The delta H is looking at the energy between our reactants and our products. Because of our diagram and implied labels behind it, we're looking reactants to our products. The products are, depending on how you want to look at it, I would argue higher in energy than your reactants, so it's endothermic. At best, it's even. Either way, we're not looking at something exothermic. Okay? And for sure, you don't want to put this on an exam because now it's questionable. Okay, so even if we tweaked this a little bit, a little bit better view and put products, yeah, that's exothermic. But now that starts to put it in a little bit of gray area that might make it more challenging for an instructor to go through and grade as you intended. So I would argue if you're going to push exothermic or endothermic, make it extreme enough that someone can't get confused by it. Okay? You could add to that diagram some more information. Your delta H is less than 0. Okay? So now you have some context that allows you to go through and say that, yes, that's actually exothermic. Make sense? Okay. So cool. Does this answer the question asked? No. What's the problem? What was the question asked? Key word in the question. The mechanism for each step. And you might be like, I don't see each step. That's because I deleted it. Okay. But that's where you were given these two steps. Okay. Why is this important? How many steps did we show? We only showed one step. Because we have two steps, our mechanism isn't correct, so we would have to adjust it. How do we adjust it? Each of our reactions happens as a peak. So if we undid this, this peak is the transition state for one reaction. If we have two mechanistic steps, we need, absolutely correct, we need two peaks. Okay? So we would need two peaks. We've got a question. Where should those peaks be relative to each other?
Maybe the slower one will be higher than the other one.
Okay? Maybe the slower one should be higher than the other one. What dictates speed? Is it just the height of the transition state?
Distance you have to go up from where you started.
From where you started. So if we look at the second one versus the first one, which one of those two reactions is going to be fastest? Step 1 or step 2? Step 2. Transition state, exact same energies, and yet it's still significantly faster because it's not starting at our reactant, it's starting at our intermediate. Okay? So knowing the exact locations of those transition states is not something, sorry, did I not?
Sorry.
Okay, I just want to make sure I didn't destroy your computer.
No, it's okay. I was hoping that was out of the way.
We want to make sure that we clarify that kind of language, and then we run into a system of, well, I don't really know. Okay? And if you don't know, don't stress about it. Nailing down the specifics of where that point is relative to everything else requires a whole hell of a lot more information that we don't have. Okay? Next thing that I would point out within this, let's just go ahead and continue with this one. Is this what everybody drew? No? How did you change it? Okay? So we can tweak the peak height We'll go ahead and make the first one a little bit bigger. Does that feel better? Okay. So now I drew exactly what you drew? Did I draw what everybody else drew? For the record, I walked around and looked at everybody's stuff, so I know you didn't. What did you change? Does this mean I'm right and you are wrong if you drew something else?
I didn't realize we had to consider both peaks because there's multiple mechanisms.
Okay, so we absolutely need to address that. We need 2 peaks. What else is different about what has been drawn? At least 2 people in this classroom drew something different than what I just drew. You don't want to volunteer? Okay, I'll volunteer you, sort of. Which is correct, the red path or the blue path? That's a hard question. Let's try a different question. Does the blue path still answer all of these statements correctly? Still 2 steps. Still an exothermic reaction. The first step is still the slowest because it has the largest activation barrier. So which one's correct? That requires more information that we don't have. Okay? And I forgot, we did address the speed, slow and fast. Okay? Which of these would I make the argument is more correct? The red one, not the blue one. Okay? I have more context than you, so don't be going, oh, I'm now horrible. You know, you did fine. Why would I say the red one is better than the blue one? What is the blue one suggesting?
That both steps are exothermic.
That both steps are exothermic. And I'm saying the first one is endothermic. But why should the first one be endothermic, not exothermic? What magic context do I have that maybe you don't? What's the product of the first step? Oxygen and oxygen. Okay, be better. The statement of oxygen is O2 by definition. So an oxygen atom and oxygen gas. Okay. What do I know about oxygen atoms? In fact, the language already gives it away. It's unstable. If it's unstable, what's its energy?
High.
It's higher in energy. So more than likely for this mechanism, that red path is more correct. Is that information that you knew coming into this? I would argue no. Okay? And so either one of those should have been perfectly acceptable. Does that make sense? Starting to get an idea behind it? Okay. I'm going to hit next and delete my image, but since you already drew images, you should be good. And I forgot. I can't hit next there. I have to hit next here. Do you think the enthalpy change of a reaction, endothermic or exothermic, affects the rate? Talk at your tables.
I mean, if it were like the same reaction.
I'm not hearing tables. I'm hearing table. We can stew. So what's the verdict? What do we think? Should the enthalpy change of a reaction affect the rate? There's something from a movie. I can't hear you. Right? That's a movie. Fine. Pretend. Do I got to point at tables? What's the verdict? Do we think it affects the rate?
Yes.
Hearing some yeses? Anybody want to challenge that and be like, the rest of the class is wrong? You absolutely should.
I was
Where's the enthalpy on this diagram?
From reactant to product.
The enthalpy is the difference between the reactant and the product energy. That's my enthalpy. Okay? If I make this an endothermic reaction, okay, my enthalpy is now here. Where's the speed of the chemical reaction? Has to do with the peak, sure, okay, which might pull something out of context right there. In referencing our enthalpies, we didn't talk at all about the peak. The speed of the chemical reaction has to do with the peak. Partly, what's the other half of it? Where are you coming from? We run most of our reactions, we consider we're coming from our reactants. If we're looking at the activation energy for this reaction, that's there. If that energy goes lower, I get a faster reaction. Where's enthalpy? Enthalpy has nothing to do with that transition state. What does that mean? Enthalpy doesn't affect the rate. Right, if you go all the way back, I know it wasn't a recorded lecture, but remember day one, we ended with day one, and I was drawing all the energy diagrams and lines and things. Kinetics versus thermodynamics. They are two separate pieces, and we have to treat them independently of each other. Kind of, sort of? Questions about that? Okay. Started to change some slides. Our homework number 2 is actually due January 26th. Officially, I have not actually checked to make sure Alex has one, but I think following based off of what you all told me, you get an Alex homework every week. Okay. A few people reached out saying they needed more time because they couldn't get registered or something like that. If that happened to be one of you, you have to reach out again. I tried to adjust times. I can only do it per individual. If I do it for the whole class, everybody loses access. Okay. So rate of a reaction is change in concentration over time. So we talked about this. Okay, we look at a chemical reactions, how our concentration changes. Okay, this is usually measured as capital M over seconds, okay, so molarity over seconds. Okay, and you could think even further and push back to the number of molecules that react per second. So if we looked at these two solutions, which of those solutions, if a reaction were to happen within them, would we expect the reaction to happen faster in? The one on the right. Why?
Because it has higher concentration.
It has a higher concentration. There's more particles there. More particles means more likely to have collisions. More collisions means we're more likely to form those products that come out of them. Okay? If we go through and look at this, we could specify capital M per second every single time. One of the things that we'll tend to get kind of lazy about when we deal with concentrations is that we stop using units. Isn't that exciting? Right? No cheers. Okay, whatever. Fine, you can keep using units. One of the things that we'll abbreviate, as you're seeing actually down here, what do these brackets mean? It's concentration. Brackets are a reference, a direct reference to molarity. Okay? So if you're seeing brackets show up in your equations, we've already implied molarity behind that unit. Okay? In order for molecules to react, they have to collide. Okay? Remember, we have other contributing factors. We need correct orientation, and we need enough energy. So if we increase the concentration of the reactants, we expect the reaction to go faster because we're increasing the amount of collisions, not necessarily the correct orientation, but if I have more collisions, probability would suggest that I'm going to get more correct orientations. Same deal with the energy to react. Okay? This is known as collision theory. Okay? So let's take a look. If the concentration of reactants doubled, what do you expect to happen to the rate of the reaction? Okay? We got lots of different answers here. Let's start as simply as possible. What should happen to the rate of the reaction? It should increase. Increase is an easier answer. A couple people said doubled, okay? Then doubled, because all you're saying is it goes up. Doubled is now saying specifically how much it went up. Okay? So should it stay the same? No, that really doesn't make much sense. Okay? Though we'll come back to that one in a second. As an answer choice, should it double? How about quadruple? Okay? And there we potentially encounter an interesting statement. It depends. The rate of the reaction is actually going to be dependent on something else than just concentration. What else is it going to be dependent on? You can't go like you had an epiphany and not be loud unless you yawned. You got an out.
Is it like the activation energy? If it's a high activation energy?
It's related to that.
Was it just time?
Is it like the reactant themselves?
How did the reaction happen? It's dependent based off of the mechanism. If you change the mechanism, that's going to change the activation energies, which is why the activations are important, and that changes the speed of the chemical reaction. So if we're looking at an individual chemical reaction, all the way, that's my slide. Okay. Whoop, come back here. Okay. Maybe it doubles. Maybe it quadruples. Maybe it doesn't change at all. Okay, which sounds extra weird. Okay. The official formal rate of the reaction is going to be dependent on how the reaction happens. That how is our mechanism. What are those individual mechanistic steps? Okay. So when we consider our rate, what we're going to encounter is a new concept of the rate law. Okay. If you take OChem with me, okay, or even later in this semester when we talk about equilibrium, we're going to come back to the rate law. So it's an important thing to be aware of. When we look at the rate law, our rate, which we could measure in brackets R, what does that mean? Concentration. What was R?
Time, seconds.
We can bring in seconds. What's R? Reactants. Okay. Or we could look at products. Typically we would look at products. Okay. Over time is going to be related to K. I don't really know what that is, so we'll come back to that. Okay, and actually we'll call this rate for our reaction. Okay, brackets A, where A is our reactant. We're going from A to B. So the rate of our reaction is going to be dictated based off of a K times the concentration of our reactants. Okay, and we've got some extra things that are appearing in this. We get a K and we get an X. When we looked at the rate of the reaction, what things controlled the rate of the reaction? If I go backwards, I delete all this work. Don't make me delete all the work. What controls the rate of the reaction?
The mechanism.
True. How do we quantify? What happens if you increase the concentration of the reactants? The rate increases. So if we're looking at the rate for our reaction, what happens if I increase the concentration of my reactant? If this value gets bigger, what should happen to my rate? Should also get bigger. So we see that relationship come out of it. Okay? This rate expression helps to tie those things. But we also see these extra two terms, the K and the X. Okay? The how is actually the X. This is how the reaction happens. This is our mechanism. Okay, and we'll come back to that X and a value because we have to quantify it somehow. What is the K? What do the brackets mean? Molarity. And what is molarity a measure of? Concentration. So it's not concentration. What is K in reference to?
Orientation.
Ah, the proper orientation of the molecule, allowing the chemical reaction to happen. For those people at home, what we're looking at is a pen trying to close. Right? So our orientation is very challenging to actually nail down and be very specific about as far as we go. But for any individual chemical reaction, what should happen to the orientation? Said another way, should the orientation that produces product change for an individual reaction?
It's constant.
It's constant, which means K is a constant. K is a constant that envelops all this stuff, this secondary material that's very hard for us to kind of control and measure, and just says for that reaction it happens all the same. I can call it a constant, and I fold it all into one giant gooey pile, and I just call it K. Okay? So those are my orientations, how much energy-ish. Okay? The big one is orientation. But there's other aspects that kind of feed into that. And ultimately, for an individual reaction type, it's constant. Okay? So, what do we mean by the how? Okay? So a first order reaction, I'm going to write the rate law again. And I want to highlight that X. That X in a rate law, we typically call the order for the reaction. It's our how, it's our mechanism. So what we're going to talk about is how could it happen? Well, in one case, we've got a first order reaction. What happens? You take one molecule. It doesn't have to collide with anything. It just has to have enough energy to go whoop up and it falls apart. That would be a first order reaction. Okay? That falling apart would produce intermediates that could then continue the chemical reaction in a later step. Okay? So if we're looking at a first order reaction that only involves one molecule, what do you think the X is going to become? 1, first order. It matches. Okay? That molecule is only needed that one time and it runs the reaction. Okay? You also get second order reactions where you can take two molecules of the same substance and you can smack them together. Okay? So if we were looking at our rate law, what does that mean? Well, if I needed both of these things, it will be colorful. Why not? Let's be colorful. I need the blue ball and the blue ball. Right? There's the rate for my reaction. Can I simplify that rate? Yeah? What can I simplify it to? Say again?
Squared. They're all squared.
And I can square it. We can now refer to this reaction as a second order reaction. Okay?
So the mechanism can be used to determine the order of the reaction?
Yep. And so this becomes the beauty of mechanistic steps, is mechanistic steps. Okay? We can determine the rate law. But if it's an unknown reaction, whether it's a mechanistic step or not, we don't know. Now we can't determine the rate law. We would have to run calculations to figure it out. But only when they're elementary mechanistic steps can we actually make these assumptions, which is kind of neat. Do the ball have to be the same color? Nope, it could be different colors. So we could run through a rate law for this one, rate K bracket, 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 bracket. And sorry, I'm going to have to switch my orders to different color now. But isn't this first order now? Because isn't that exponent 1? Shouldn't that be a first order reaction? Say again?
Yeah.
It is first order with respect to each reactant, but there's two reactants. So the overall is the sum of the exponents. It still comes out to be 2. Make sense? Cool. What happens if I add a third ball? What would happen to my order now? Is it second order anymore? No, what is it?
Third order?
Third order. What if I add a fourth ball? As soon as you said that, I was like, I have no idea how to answer that question. Would you call it quadruple order? Yeah, I'm okay with that. Let's go with quadruple order. How about a fifth ball? 6, 7. So we can have an infinite amount of reactants involved in a rate per chemical reaction. Okay. Remember, what's happening in these steps, these are elementary mechanistic steps, is all of this happens at one exact instant. What is the likelihood that I take 100 balls and I get them to all hit at the exact same energy, correct orientation to form the product? What's the probability of me being able to pull that off?
Unlikely.
Yeah, it's very unlikely. Which means, does it make sense to look at a 100th order reaction?
No.
No. So if 100th order doesn't exist, and first and second order does, how about 99th order? Should that work? No, take one down, pass it around. 98th? Come on, that was kind of funny. 90th. Where's the line? Okay, well, always with the great examples that are inappropriate, so let's go ahead and run with that. We talked about chemical reactions as individuals, right? Okay. Can an individual go through and do something successfully? Yeah. Can partners? So we were like, well, no. You work in the lab and partner, and that's why you're saying no. Okay. You work in the lab as partners. Okay. So that's, how about 3 people? That is an appropriate grumbling sound to make. As soon as you bring 3 people together, it ends up not working very well at all. You get one person doing, one person writing, and one person watching everybody else do it. That doesn't work, which is why in lab we do partners of 2 instead of 3s or 4s. So what does that suggest back to our chemical reactions? Does a third order reaction make much sense? Nope. And so we stop at second order. Okay. Does that mean third order can't happen? No, it can, but that should be a last resort. I've tried to explain this reaction through first and second order, and it didn't work. So now I'm going to try to explain it through third order. Does it match the data? Okay, well, dang, I found something that it works for, but it's insanely rare. Make sense? Cool. So, write the rate law for this reaction. Okay? And talk to the people around you. Speak up, sir. What's your complaint?
Oh, no, I thought we were talking about favorites.
Fine enough. I called you out anyway.
I don't know, I just see one thing on the first side, one thing on the second side, which is,
Well, there's 2 things.
and 3 things technically, yeah.
3 things.
So you could go through and count the amounts. So we could go through and say, well, I would call this rate equals what? K, good. That's supposed to be a lowercase k, which will be relevant later on in the semester. Concentration of ozone, our reactant. And then how important was it? Was it a first order reaction, second order, third order? What information do I need to know what that is? This is what you said, and then you backed away from it. I did it again.
I'm sorry, is this?
No, it's not your fault, it's me. To answer the question, what do you need to know?
The mechanism.
You need to know the mechanism. The mechanism is what's going to dictate this, which is why I frantically erased it. Now you can have your conversation. Okay. So one of the things that we jumped on right away, and I said we had to be careful of, is we tried to write the rate law for the top reaction. Okay? That top reaction does not work to determine the rate law. We can't pull the coefficient out of that equation because we don't know how that reaction works. Okay? We don't know the mechanism. That, too, comes from the mechanistic understanding. Where's the mechanism? That's what's underneath. So if I want to understand how this reaction occurs, I need to look at the rate laws for the individual mechanistic steps. So I could go through and look at those 2 rate laws. I get rate equals K times the concentration of ozone. Okay, to what power? The first power. That number is now allowed to be used. I can do that. Okay? In the top case, it was a question mark. I can't use it because that's based off of the mechanism. As soon as I move into step 1, that's a mechanism. Now I know the order of the reaction. It's from my expression. What happens for step 2? What will my rate equal? You were presumably going to ask a question, right?
No,
Oh, okay. Go ahead. Answer.
the K bracket O to the 1, and then bracket O3 to the 1.
I'm allowed to pull those orders out because I'm looking at a mechanistic step. Only when I look at a mechanistic step can those orders be pulled out. That's the point of our mechanistic steps. Okay? Overall reaction, unclear. Maybe, maybe not. Okay? Elementary mechanistic steps, yes, I can absolutely use them. Okay? But the question still comes back to, I want the overall rate. I want the rate in black. What's going to control the rate of the black reaction? Or what I'm calling the black reaction. Say again? The slowest step dictates the rate. The fast steps are just going to happen incredibly fast. I don't care about those. I only care about the slow step. So what does that mean? The rate for my overall reaction is going to be K times the concentration of ozone to the first power. That's it. The mechanism gives me that information. Kind of, sort of? Should we make it harder? Not yet. What's the question?
I was asking if this is the net. Are we saying that K ozone? Are we saying that this is ultimately the rate law for the overall reaction?
Rate in black, so if we sort of color code these, we're calling this one our black reaction, our red reaction, and our orange reaction. So the rate law for the red reaction is as such. For the orange reaction is as such. Okay? If we start at the very beginning, trying to determine the rate for the black reaction, what we're saying is we don't know because I don't know how it happens.
Okay.
As soon as I define how it happens, I can now look at those slow steps and I can say, what would the rate law be? Okay, so I look at those steps and say, which one's the slowest? By looking at those and finding out which one's the slowest, that one controls my rate. My rate is now equal to K times, or my rate constant times concentration of ozone. Interesting question. I'm honestly not 100% sure how to answer this. But let's see what you guys think. Do you think the black K and the red K are the same thing? It is a constant. Okay, R is a constant, right? R, gas law, constant? Yeah? How about, I need another constant. Boltzmann's constant? You guys know Boltzmann's constant? Speed of light, there we go, C. Both of those are constant. Does that mean their numerical values are the same? No. In the individual context that we use them, it's constant, okay? But that does not mean all constants are the exact same value. So again, back to this, would we expect the red rate constant to be the same as the black rate constant? You say no, why?
So it made the rate law for that step the same as the overall rate law, which just doesn't really make sense.
I would kind of agree with you. There's more going on with the black reaction, okay, that's going to get tweaked slightly. Is the red rate constant going to be close to the black? Probably pretty close, okay? Because we're saying the orange one happens so fast it was irrelevant, okay? But it's going to have some slight effect within there. So I would argue, yes, they're different, but they're probably not that different. Okay? We ready for a monkey wrench? Yeah, we love monkey wrenches. Actually, not yet. One more question. Am I reasonably expected to know the concentration for ozone? O3. So some people are stewing on that, while some people are stewing on it. Other people have already stewed on it. What was the answer? Why would I already know ozone? So yes, that's something I'm expected to know. Now you don't have to answer, thank you. Why am I reasonably expected to know the concentration of ozone?
You're observing the reaction.
Gets to it, look at your overall reaction. Where does ozone show up in the overall reaction? As a reactant. Where do the reactants come from? From me. I'm the chemist. I put them together to make said reaction. So yes, I should know the concentration of the reactants. That's a reasonable statement to make. Make sense? Okay. Monkey wrench. What do you think the monkey wrench is? What do we do? What did I do?
Would the overall reaction be the second step then, because it's the slowest?
Right? Drawing the conclusion, all we did was swapped which one was the slow step. So instead of the slow step running first, we ran it second. Okay? How would we know that? We have to go to experimental evidence. So this isn't just me like, oh, it must be the slow step. Experimental evidence gives us this information, but if information spit out and said this was the case, what becomes our overall rate law? And now I will ask again that painful question. Am I expected to know the concentration of oxygen atom? Look at my overall reaction. If you're like, but it shows up as a reactant. It does show up as a reactant, as a product, as an intermediate, meaning I mixed the stuff together, stuff happened and it produced this thing and then it ate that thing and it produced it and then it ate it and it produced it and it ate it, which meant I have no clue what its concentration is. So what happens now? Is this rate law now useful for me? No. And that's where we have to add extra rules into this system. Those extra rules have to go back to referencing how we determine the concentration of that oxygen atom. Okay? That's a significantly harder question and one that I don't think is in store for right now. So we're going to let that one go, but I want you to realize that we do encounter an issue. Does that make sense? Okay. If it shows up in active, let me know. Today's Tuesday. Yeah, let me know on Thursday. Okay. So what happens to the rate if the concentration of ozone were doubled in this case? What was our correct overall rate? So it was that one. What happens to the rate of the reaction if the concentration of ozone goes up by 2?
Goes up by, it's doubled.
It doubles. What if I quadruple the concentration of ozone? It quadruples. You're just doing a direct substitution into your rate expression. Okay? If our rate expression said it was second order, what happens to the rate when it doubles? So now it's not going to double because I'm changing that O3 value to a 2. 2 to the second is 4. Now it quadruples. Does that kind of make sense? So you're manipulating how the rate law affects your overall rate. Okay? So write the rate law for this reaction. What would happen if the rate of the concentration of HI were doubled or tripled? So you got a bunch of questions here. We'll give you a little bit of time. So what's the rate law? Yes, sir.
We had a disagreement, I'd say.
Ooh, lovely.
So some of us said that we thought it was K bracket HI to the 1. Well, I think all of us thought that was the rate law. But then we see the 2 on the left side of the HI. So we were kind of arguing whether some of us thought it was doubled and tripled, but then with that 2, some of us thought it was quadrupled and then.
Cool. Which is a question that happened up front too. So if we're looking at what is the meaning of that 2. So first off, in our rate law, the thing that shows up in the brackets is just the reactant. 2 is not a reactant. Okay, it's a modifier of said reactant. Did you get it? Okay, so the 2 doesn't show up within the brackets. The question now becomes is where does that 2 show up? Should it show up? When we looked at the ozone, did it show up? If I remember, the ozone was 2 ozone became 3O2, right? And we said, with more information, that was our rate, right? So the 2 didn't show up. Why did it not show up?
The 2 is there for the concentration amount and to balance the equation.
Up here, why did the 2 not show up?
Two-step reaction.
Okay, that superscript, our order for the ozone came from the mechanism. We had to look to the mechanism to tell us what the order should be. And we look at the ozone example, our O3, that wasn't the mechanistic step. We had to look at mechanistic step detail. Does this question change? Why does it change?
It doesn't have mechanistic step, it's just got the one step.
It's saying that this is a one-step mechanism, okay? Which is effectively implying that this is a mechanistic step. And if it's a mechanistic step, what happens to that 2? Written a slightly different way, for this reaction to happen, we have HI plus HI. What has to happen?
To the second power.
It must show up twice, which then means to the second power. You have to have that extra piece of information. That extra piece of information is being specified and saying that it's a one-step mechanism. You aren't doing a bunch of other steps. You have to take these pieces together and slam them to make this work. Okay? Is that obvious? I would argue, hell no. Okay? But you have to look for those subtle clues to help tip you off.
So we said for the ozone example that the rate law was still, we said it was still O3 to the first power, right?
Why?
Well, that's why I'm asking, why is that the case if in that ultimate reaction there's 2 O's?
What happened in the previous reaction?
The previous reaction, the slow reaction only took 1 of the 3.
You were given more mechanistic information that said how that happened, which set us up to then look at the slow step of that mechanism. Here you're told there is only one step. If there is only one step, HI has to collide with HI.
Okay.
There is no other way to do it. This is being specified effectively as a mechanistic step. So what happens to the rate of the reaction if HI is doubled? Quadruples. If it's tripled, it's six-doubled. Close enough. Actually, that's not very close at all. In fact, that's pretty horribly wrong. What's that? What happens to the rate if the concentration of HI is tripled?
It's
What's 3 to the 9th power?
3 to the
I answered the wrong question. What's 3 to the 2nd power? 9. It was 9 tupled. Nintupled? Nonatupled? Went up by a factor of 9. Okay? So be careful on how you translate that number through that calculation. Does that make sense? We good with that? Okay? What? Did I not push down? Okay. Yeah, weird. So how do we figure out the rate law if we don't know the mechanism? Oh, should not have kicked it. I apologize. So officially, you can't write your rate law from the overall reaction. So you have to have some more context. Okay? This is very, very, very challenging because the big lesson that kind of comes out of that is that the coefficients don't match. Okay? So if we're looking at ozone to O2, what was the rate law? K times O3. But if we looked at the HI one, what happened? I don't even remember the products. What were the products? H2 and I2?
Yeah.
The 2 did come out. The 1 did not. Right? And this becomes one of those very misleading things. As you look at a reaction, you go, oh, I can use the coefficient as my order. No, you cannot. But I can. What's different? You have to know that it's a mechanistic step. When it is a mechanistic step, you can use the order, okay, as your coefficient. But that must be true. Every other scenario, it is not necessarily true. Could it still be true? Yeah, but not necessarily. And that becomes the mismatch. You try one question where the coefficient is the order, you go, oh yeah, I can just do this. Not always. Okay? And if an exam question is written really well, you might even see a run of questions where it matches, and then all of a sudden it doesn't. Why? Are you falling into a natural trap of just, oh, I can just copy it across? You can't just copy it across. Okay? To figure it out, what we would go through and do is run a bunch of experimental conditions. We would start with different concentrations of our reaction, and we would change or run the reaction. Monitor the rate of the reaction, and then start to make comparisons between it and see how the reaction changed with respect to the concentration of our reactants. Okay? That gets us to our rate law. We don't necessarily know the mechanistic steps, but we would have a rate law that describes the overall reaction. Okay? So you measure your initial rate. You figure out your initial rate because you know a chemical reaction has happened. How do you know a chemical reaction has happened? Those people are like, I'm looking right off the slide. How do you know you have a chemical reaction?
You can observe some.
How do you know? I look at a thing. Did a chemical reaction happen? Color change. Phase change, formation of solids, temperature changes. Okay? You could look for those systems. Some of those become trickier to quantify, like a temperature change. It's going to start to form energy or release energy in that reaction, but is it measurable yet? Okay? So coming up with a system that allows you to quantify the energy of your products as you run becomes challenging. Okay? You can also run different forms of spectroscopy, and there's lots of science out there now about how to run that. Okay? And then what we would do is say, well, how did the reaction change? Okay. This is an empty slide that I've got zero context on, but based off this information up here, what do you think this is trying to do? How would we calculate the rate change, concentration over time? This is determining how do I figure out the number for rate. Right? You can say, well, it's the rate constant times concentration of your reactants. Well, what's the rate constant? I need a numerical value. Once I have a numerical value, I could then solve for the rate. That's flipped. I need to know the rate before I can solve for anything else. How do I figure out the rate? Well, what is rate a measurement of? Say it again? Cool. How am I monitoring the progress of the reaction? Okay, over time. So how do I figure out a change in time? Time final minus time initial, okay, which we would hope to be in seconds. I'll write out that one. What do we do for the numerator? Okay. We could look at the molarity initial, and we could compare that to the molarity final. So we would need a way to quantify those values. Where are you going to have to do something like that? I think I heard it mumbled. In lab, that's where you're going to do it. Okay, so lab will have you go through and test some rate law stuff by monitoring a chemical reaction, and you're going to be changing concentrations, and you'll be monitoring the initial and final concentrations to come up with a system like this. If we were looking at the reactants, final minus initial is going to give us a what magnitude number? If I look at reactants. A negative value. Your final concentration of reactants should be smaller than your initial. So you would get a negative value. We'd have to take that into consideration and drop that minus sign. You remember that was last week's lecture where we looked a little bit at that. So typically what we would do is monitor the progress of our products, okay, because that's evidence the chemical reaction has happened, and that value should at least be positive. Kind of, sort of? Cool. So cool. What is the order with respect to CH3,3CBr or tert-butyl bromide in the rate law? What is the order for hydroxide? So we've got our overall reaction, and we now have all of this data. It's kind of a hard question. See what you can come up with. I see a blue box, so you're supposed to think about it. You do not have to calculate it. Walk through the process of what you would do. We're done at 11:15, right?
Yeah.
Cool. Cool.
What number slide is this?
I've got it marked as 35. I don't think I've added any new slides, so it should be slide 35. Her slides weren't initially numbered, so I had to drop in numbers so I knew where I was at. It was a good question. This is slide 35. I've got numbers on the slides. If you look at the slides that you downloaded, they don't have numbers on them. Just be kind of aware of that. Oh, I should have paused that. In the interest of time, sorry, I'm going to skip over your question. We're going to address experiment 1 and 3. So what we're doing is now only focusing on experiment 1 and 3. So I have no care at all about what's happening with 2. Okay? I'm trying to compare what's happening in those two situations. Okay, so I could start left to right, because we read left to right. What happens to the concentration of CH3CBr? Stays the same. What should happen to the rate? It should stay the same, right? Because I'm not changing that one, the rate shouldn't change. What happens to the hydroxide? It doubles. So we could quantify it, which will become relevant later, or we just say it increases. Okay? So if we say it increases, what should happen to the rate? It should increase, right? Okay? And extra fun, because I didn't change the concentration of the first species, the change in rate is only due to the hydroxide. I've limited a variable. What happened to my rate? So is hydroxide involved in my rate? No, because if it was there, it would change the rate. It didn't change the rate, which means can't be involved in my rate law. Okay, so I'm comparing experiment 1 and 3. Hydroxide increased, rate stayed the same. The order with respect to the hydroxide must be 0 order. Cannot show up in my rate law. Anything to the 0 power is going to be 1, so it has no effect. Okay. What does that mean about the CH3 thing? Okay. It has to have some effect on the reaction. Otherwise, how is a chemical reaction happening? But the question becomes is how? Is it first order? Is it second order? Okay. How do we figure that out? Okay. So I'm going to do a similar system, and I want to find 2 experiments to compare. Okay. Let's pick 2 and 3. Are 2 and 3 a good experiment to compare? You already figured out the answer, so you don't count. I mean, you do, but should I compare experiments 2 and 3? You actually heard the answer.
No,
No, thank you. Okay, why not?
because we know that OH doesn't, the concentration of OH does not affect the rate of the reaction.
Nah. Why should I not expect?
Like everything has changed.
Yeah. The whole point of this is to limit your variables. If you compare 2 and 3, both reactant concentrations are changing, which then means the rate change at the end, which one was it due to? Right? It could be due to either of them or both of them. Because you know hydroxide isn't, you could ignore the hydroxide. Okay? And that is a fair statement to make. But you're now combining not just picking 2 experiments, but also information you learned. What if you hadn't compared experiment 1 to 3? You now don't have that context. So what 2 experiments are a better comparison? 1 and 2. And if we look at 1 and 2, what happens to the hydroxide? It stays constant, which means it's not affecting the rate at all. Look at the concentration of our CH3 guy. What happened? Simply, what happened? That's not simply. It increased. What happened to my rate? It increased. Cool. Now I should quantify. How much did my concentration increase? Doubled. How much did my rate increase? Doubled. What does that mean the order has to be? Okay, and we got a lot of people saying second order. So this is the fun thing that's not confusing about chemistry. Guess and check. If this is my rate law, right? What happens if I double the concentration of CH3 thing? The rate quadruples. Did it quadruple? No. Is it second order? No. What's the order? First order. Whoops, sorry, there's words behind it. What's your rate law? Ta-da! The experiment tells us that's the rate law. Why is this powerful and useful? Okay, well, now we have an expression, and with that expression, we could now go, well, what are possible mechanisms? Well, there's 2 possible mechanisms. I could have had the CH3 compound and the OH go smashing into each other and produce the products. That's one mechanistic step. Or I could have had the CH3 bromine thing just be like, I'm going to fall apart. Produces an intermediate. That intermediate then smashes into hydroxide. So I get 2 mechanistic steps. Which of those mechanistic steps best represents the rate that we defined? The second mechanism. Whoa! We went from just random mumbo-jumbo confusing numbers to now saying how the reaction happens. First, you had to break off the arm before you put on the robotic arm. That's kind of neat. Right? So you're looking at how that applies and how that stacks out. Those individual mechanisms, I don't know what Dr. Schneble is going to ask you. I don't know if she's going to expect you to be able to predict what are possible mechanism routes. I would expect not, and she's probably going to give you multiple mechanisms and say, which of these explains the data? Because that's a pretty awesome question, personally. Right? I know we're done. How would we figure out the rate of the rate constant? Or sorry, the value of the rate constant? Yeah, the rate constant. You said the answer, but then you made sounds afterwards, making me think you didn't agree with the answer, but it is that. It's plug and chug. Right? Once we know what the rate is, or the rate expression, you know the rate value, you know the concentration, solve for the rate constant. Sorry, you're done. I'm done.